black holes are among the most mysterious and perplexing phenomena in the cosmos, captivating the attention of scientists, particularly astrophysicists and physicists, who continue to explore their intriguing properties. These cosmic objects are defined by their immense gravitational pull, which is so powerful that it prevents light from escaping, making them invisible to direct observation. They represent a boundary beyond which the laws of physics as we know them no longer function. The concept of black holes was first hypothesized by Albert Einstein in 1916, a result of his theory of general relativity. However, black holes remained a theoretical concept until the 20th century, when advances in technology made it possible to indirectly detect them. The key moment in the study of black holes came in the 1960s, when astronomers investigating the Cygnus constellation stumbled upon a unique celestial object. This object, a brilliant blue star emitting intense X-rays, was discovered to be in orbit with an unseen companion. It was later identified as being in a gravitational relationship with a massive black hole, now known as Cygnus X1. This discovery was pivotal, providing strong evidence for the existence of black holes and opening a new chapter in astronomical research. Cygnus X1, located about 6,000 light-years from Earth, is a particularly extraordinary black hole. It is incredibly dense, exerting a gravitational force so immense that even light cannot escape its pull. This defining feature led to the term black hole, encapsulating the essence of these enigmatic objects. Subsequent astronomical surveys have revealed numerous black holes scattered throughout the universe, with estimates suggesting that the Milky Way alone may harbor more than 100 million of them. Despite their elusive nature, which complicates direct observation, scientists have been able to identify several candidates within our galaxy. These range from stellar mass black holes, formed from the remnants of massive stars, to supermassive black holes found at the centers of galaxies. The gravitational influence of these black holes extends well beyond their immediate vicinity, playing a significant role in shaping the formation and evolution of cosmic structures and influencing the fate of surrounding matter. Objects that come too close to a black hole are subjected to its relentless pull and are drawn inexorably toward the event horizon, the point beyond which nothing, not even light, can escape. Once past this boundary, objects are subjected to extreme tidal forces, eventually being consumed by the singularity at the core of the black hole. This process, known as spaghettification, occurs because the gravitational forces exerted by the black hole are so extreme that they stretch and distort objects, pulling them into a long, filament-like shape resembling strands of spaghetti. These forces overpower the internal cohesion of the object, causing it to disintegrate and merge with the singularity. While black holes present exciting opportunities for testing the limits of physical theory, they remain shrouded in mystery. The pursuit of understanding their secrets continues, fueled by the desire to comprehend the nature of space, time, and gravity. In the vast expanse of the universe, black holes serve as silent guardians, drawing humanity's curiosity to explore the depths of the unknown. Despite the vast distance between us and the closest known black hole, around 1,500 light-years, concerns about their potential impact remain, especially in the context of understanding their role in the cosmos. In 2021, researchers achieved a monumental breakthrough by capturing the first clear image of a black hole, specifically M87, which resides at the center of the M87 galaxy. This remarkable achievement provided crucial insights into the structure of black holes, revealing that they are far more complex than previously thought. The data captured showed that black holes are not simply dark voids, but instead have intricate layers. Through detailed analysis and the combination of images, scientists identified 3 distinct layers within a black hole. At the outermost layer lies the event horizon, marking the point of no return for any object that crosses it, where the gravitational forces become insurmountable. Further inward, the photon sphere is the second layer, where light becomes trapped in orbit around the black hole. Any photons that venture into this region are unable to escape, remaining perpetually bound to the black hole. At the core of the black hole lies the singularity, the third and final layer, where the known laws of physics break down entirely. The familiar rules that govern the universe cease to apply, pushing researchers into a realm of deep uncertainty and speculation. The inherent complexity and variability of black holes present significant challenges to our understanding, as each one behaves uniquely, making them difficult to categorize. This has led scientists to adopt innovative approaches to study these cosmic giants, as traditional methods of observation and inquiry are not sufficient to reveal all their secrets. Indirect observation remains the primary way to study black holes, as direct investigation is virtually impossible due to the overwhelming gravitational forces that they exert. Attempts to send probes into black holes would be doomed, as they would inevitably be crushed into oblivion by the immense forces at work. Nonetheless, researchers continue their pursuit, driven by the hope that these enigmatic objects hold the key to answering some of the most fundamental questions about the universe. Various theories, from stellar collapse to cosmic dynamics, provide tantalizing insights into the origins and behavior of black holes. NASA's exploration of the cosmic center of M87, for instance, uncovered strong evidence of a supermassive black hole influencing its surrounding galaxy on an enormous scale. Despite these challenges, the search for knowledge remains unyielding. Humanity's inherent curiosity continues to push the boundaries of science, with the study of black holes promising to expand our understanding of the universe. One of the most groundbreaking contributions to black hole theory came from Roy Kerr in 1963, when he proposed a theory about rotating black holes. Kerr's work introduced the concept of the ergosphere, a region surrounding a rotating black hole where forces balance the gravitational pull, preventing matter from collapsing inward. This idea was a dramatic departure from traditional models, suggesting that black holes might behave in more complex ways than previously thought. Perhaps the most intriguing implication of Kerr's theory was his prediction of an Einstein-Rosen bridge, informally known as a wormhole. A wormhole is a hypothetical structure that could act as a shortcut through spacetime, potentially connecting distant regions of the universe or even alternate realities. The concept of a wormhole arises from the interplay between Einstein's theory of general relativity and the fabric of spacetime, which is warped by massive objects. In this framework, wormholes would serve as tunnels through spacetime, offering the possibility of rapid travel across vast distances. However, the feasibility of wormholes remains a topic of intense debate, with significant challenges standing in the way of their realization. While wormholes offer tantalizing possibilities for interstellar travel, their stability and practical use remain highly speculative. The inherent instability of wormholes, combined with the immense challenges posed by quantum forces and radiation, makes it unclear whether they could ever function as viable transportation routes. Furthermore, Einstein's theory imposes strict limits on how quickly objects can move through spacetime, suggesting that even if stable wormholes were discovered, they might not allow for faster-than-light travel, a staple of many science fiction stories. Nevertheless, the idea of wormholes remains a subject of great interest, inviting scientists to explore the mysteries of space and consider the infinite possibilities that might exist beyond the known universe. The search for a unified theory of physics that reconciles gravity and quantum mechanics has led to the development of various theoretical models. At the forefront of this effort is physicist Michio Kaku, whose work on superstring theory has made significant strides in explaining the fundamental forces of the universe. Superstring theory proposes that particles, rather than being point-like objects, are actually tiny, vibrating strings. These strings resonate at different frequencies, giving rise to the various particles and forces that we observe in nature. In this view, the universe can be likened to a vast symphony, with each particle representing a unique harmonic frequency. One of the most exciting prospects of superstring theory is its potential to explain the phenomena associated with black holes, wormholes, and other exotic solutions to Einstein's equations. As strings move through spacetime, their interactions could lead to the formation of gravitational singularities and other anomalies. However, superstring theory is highly complex and requires the existence of extra dimensions beyond the familiar 3 spatial and 1 temporal dimensions. These additional dimensions are hidden from direct observation, but their theoretical presence could explain many of the strange phenomena observed in the universe. Despite the challenges posed by the hidden nature of these extra dimensions, superstring theory offers promising solutions to some of the deepest questions in physics. The mathematical framework underlying the theory has also sparked a renewed interest in mathematical physics, revealing connections between abstract mathematical patterns and physical phenomena. Nevertheless, superstring theory remains largely untested, with experimental verification remaining a significant hurdle. The elusive nature of the extra dimensions involved makes it difficult to test the theory directly, relegating it to the realm of theoretical speculation for now. In conclusion, while superstring theory offers a potentially elegant and comprehensive framework for understanding the universe, it remains an unproven hypothesis. However, its bold vision continues to captivate the scientific community, inspiring new lines of inquiry and pushing the limits of our understanding. As scientists continue to explore the nature of black holes, the search for a unified theory of everything remains one of the most exciting and challenging endeavors in modern physics. Through these efforts, we may one day uncover the profound secrets hidden within the cosmos and gain a deeper understanding of the nature of reality itself.